Okay, let's start and continue with our considerations on symmetry within crystalline solids. So in the last class, we learned about the 7 crystal systems and the 14 primary lattices that there can be in 3-dimensional extended solids. And we have also seen that there are some restrictions with regards to the symmetry operations and symmetry elements in extended solids. So we have seen that with regard to proper and improper rotational axes, we can only have, well, two-fold axes, three-fold axes, four-fold axes, and six-fold axes. But not anything more than that. And that limits the number of point groups that you can have in a crystalline solid. And you can actually have no more than 32 point groups because of that reason. Now, on the other hand, however, there are some symmetry elements and symmetry operations in extended solids that do not exist in molecules. And these are the glide planes and the screw axes. And I would like to discuss these now. So let us first look at the glide planes. So what do we mean with a glide plane? So the definition is that a glide plane is a symmetry operation describing a reflection in a plane followed by a translation parallel with that plane. Okay, so as you carry out the symmetry operation around that glide plane, well, that will leave the crystal unchanged. That means that basically the produced crystal is indistinguishable from its original form. Okay, that's always the criterion for symmetry operation to be present. So now there are different types of glide planes. They are called A, B, and C glide planes. There are, in addition to that, N glide planes, and there are D glide planes. So now let us go through these symmetry elements step by step. So for instance, let's start with a C glide plane, which is schematically depicted here. So when we have a C glide plane, then that means that we have to glide along Z, and that means that we have to translate our atom within the crystal in the C direction to some extent. So this is actually shown here. So we have here our atom. So we have to glide it along the C direction when there's a C glide plane present. Okay. So after that, we have to reflect it at a plane. Okay. And that plane must contain the C direction. Okay, the translation must be parallel with the plane. Okay, that means that we now either need to reflect at the AC plane, as shown here, or the BC plane, which would be this plane here. Okay, so in this example, we reflect at the AC plane. Okay, so that means that after we have translated our atom in C direction, we reflect it at an AC glide plane, or a glide plane containing the A in the C direction, and move it to the other side. So the final position of the atom would be this position. Okay, there, of course, it would have to superimpose an atom which was previously at this position, and the atom which was originally in this position would have been moved by the glide plane into a new position as well. Okay, So now from that, we can easily derive what an A glide plane would do. So here's an example for an A glide plane. So in this case, we first have to translate into A direction. Okay. And after that, we would have to reflect either at an AC plane or at a BC plane. So in this case, we reflect again at the so either at an AC plane or an AB plane. In this case, we again sorry, reflect at the AC plane. Okay. So you see that in this case, we first move this atom along A, okay? And then we reflect at the AC plane, bringing the final atom to this position if we start out from that position. So Tom has raised a hand. Can you please unmute yourself and speak?
Yeah, I just wanted to ask if, so you said it could be either in the AB or the BC plane. Is there any way to determine that via notation, or they're both B glides, and then would it just be intuitive which one's which, or?
Yeah, basically the crystal structure would give you that would give you that information. Okay, so you would draw the glide plane into the crystal structure according to the crystal structure. Okay. So let's say you have a crystal structure. Okay, then you can draw your glide plane into the crystal structure.
Okay.
So, yeah. So that defines what glide plane it is, because the direction along which you have to translate defines the name of the glide plane.
So if you were to ask the question, just stating there's a B glide plane would be enough. You wouldn't have to say AB or something like that.
Well, if I asked you for the definition of an A glide plane, then the correct answer would be that you would have to translate along A and then reflect either at an AC plane or at a BC plane.
Okay.
Okay. Or I could give you a crystal structure, and I could tell you, well, which glide plane within that crystal structure can you identify? Okay. And then you would draw that glide plane into the crystal structure and then determine, well, what kind of glide plane it is. Okay. And again, in which direction you would translate would determine what glide plane you actually have.
Okay, thank you.
Okay. So a B glide plane is not shown here, but according to the definition, we would have to translate along B and then reflect either at the AB plane or at the BC plane, okay, depending on the exact crystal structure. Okay, so now what is an N glide plane? So when we have an N glide, then that means that we glide along the half of the diagonal of a face. Okay, and then we again reflect at that particular plane. Okay, so basically an example is shown here. Okay, so here we actually glide within an AC plane, okay, and we glide half of the diagonal of the face in which that AC plane here lies. Okay, and then we reflect at the respective face to the other side. Okay, so last but not least, there is a D-glide plane also possible, and then you translate along the fourth of either a face or the space diagonal of the unit cell. Okay, and then you reflect. Okay, so the name D-glide plane is derived from diamond, because diamond contains D-glide plane, but of course the diamond structure is not the only structure that can contain a D-glide plane. So here's just an example to illustrate this. And again, the screen doesn't move. I don't know why this happens. I don't know why I cannot move the screen. It has happened already multiple times. In this case, I cannot even get out of my PowerPoint presentation. Next. Ah, here. Okay, this way it works. Okay. Now you see here the unit cell of diamond. And diamond has a face-centered cubic unit cell. So that means that the carbon atoms, they are sitting on the corners of a cube. And the faces are all centered. Okay. See that here and here. But in addition to that, you also have 4 carbon atoms inside of the cell. Inside of the cell, you see that here, and here, and here, and there's a 4th atom here. Okay, so these atoms, which are inside of the unit cell, okay, they're surrounded tetrahedrally by 4 other carbon atoms that either sit on the corners or sit on the faces. You see that this carbon atom, which is inside of the unit cell, is surrounded by these 3 that are sitting in the centers of 3 faces, and that 4th one, which sits on a corner. Okay, and the same is true for the other 4 carbon atoms as well. All right, so where do we have our glide plane? So you see that the glide plane is here. It sits actually at the position 7/8 BC. Okay, so that means that we have to go 7/8 fractional coordinates in A direction, and then the B and C coordinates are variable, okay, defining the plane. All right, so now if that symmetry element is present, then that means that when we carry out that symmetry operation, after that symmetry operation, the crystal structure must be indistinguishable from our original form. We can test that for 1 atom. Okay, so let's put ourselves, for instance, on that atom. So we have to, in this case, translate a quarter into B direction, and then a quarter into C direction. Okay, and then we reflect at the glide plane here. Okay, and after that, basically our atom is here. Okay, and it is in a position where now in a position within the unit cell. Okay, so it moved from the corner to a position within the unit cell. Okay, so now if we did that exercise with all the other atoms, again, we would see that the final position of the atoms superimposes an original position. So the symmetry operation is complete, proving that our symmetry element is really there. We can even carry out that symmetry operation a second time. So we can put ourselves on this atom inside of the unit cell. Okay, and then again move it by a quarter into A direction, and then a quarter into B direction, and then reflect. And then our atom would actually be on this position, which is now in the center of a phase. All right, so you see again that the produced crystal structure is superimposable to the original one, meaning that the symmetry element is there. Okay, so this is meant what is by a diamond glide plane. Okay, so now in addition to glide planes, we also know what is called screw axes. And in a screw axis, a rotation is combined with a translation. Okay, so now we have learned that we can only rotate by 180 degrees, 120 degrees, 60 degrees, or 90 degrees, because only 2-fold, 3-fold, 4-fold, and 6-fold rotational symmetry is allowed. Therefore, the number of screw axes that are possible is restricted to those having 2-fold, 3-fold, 4-fold, and 6-fold symmetry.
Is a 2-fold screw axis similar to a glide plane?
No, it is not. It is not. Rotation is different from reflection. So therefore, these are distinct from each other.
Okay, thank you.
So we know actually these glide planes that are being listed here. So you see that these glide planes have a number and a subscript number. So the first number indicates, well, the order of the axis. So 2 means a 2-fold axis, 3 means a 3-fold axis, 4 means a 4-fold axis. Okay, here we would rotate around 180 degrees, here around 120 degrees, and here we would rotate around 90 degrees, for instance. Okay, then what does the subscript mean? The subscript indicates the translation. Okay, so we always translate by 1 over the order of the axis, or by the number divided by the order of the axis. Okay, so here the number is 1. So this means that for this screw axis, we translate by 1 over 2. Here we translate by 1 over 3. Here we translate by 1/4. And here we translate by 2/4, which is equal to 1/2. Okay, and these numbers mean fractional coordinates into the direction of the screw axis. Okay, so here we translate by 1/2 of the lattice parameter in the direction of the screw axis. So here we translate by 1/3 of the lattice parameter in the direction of the screw axis. Here be by 1/4, here by 2/4. Okay. So now, how many screw axes can we actually have for a particular order? So when the order is 2, then there's only 1 screw axis possible. Okay. When the order is 3, then there are 2 possible. That's the 3, 1 and the 3, 2. Okay, so now by definition, we always rotate again counterclockwise. Okay, so therefore the 3-1 would be associated with the counterclockwise rotation, whereas the 3-2, while at the first, would also be associated with the counterclockwise rotation, but we would translate by 2/3 of the lattice parameter B, by the lattice parameter, which corresponds actually to a translation into the opposite direction. Let us go through that step by step. So let us look as first at the 3-1. Okay, so here we put ourselves on a position within the crystal. Okay, so now the symbol for a 3-1 axis is this one here. So you see it's a triangle that has propellers. Okay, and the propeller is left-handed, indicating the 3-1 screw axis. By the way, for the 2-1 here, the symbol would be this one here. Okay, so this would indicate a twofold propeller. Okay, so now what will happen with this atom here as we carry out the symmetry operation? Well, of course, we would need to rotate by 120 degrees, and then we would have to translate by 1/3 of the unit cell parameter. Okay, so this is indicated here by 1/3 plus. Okay, then our atom would sit here. Okay, note that it's not sitting in the same plane as this one, but elevated relative to this one, exactly by 1/3 of the lattice parameter. Okay, then we rotate further counterclockwise, and then our atom is here, but we also have to translate by another 1/3 of the unit cell parameter, okay, which now overall gives 2/3. So relative to this atom is rotated by 240 degrees and shifted by 2/3 of the unit cell parameter in the direction of the axis. Yeah, Tom.
So if I'm looking at this right, is a 3-1 rotated, 1/3, and a right-handed 3-2 rotated 2/3 the same thing? And if so, why do we need both notations?
Because the symmetry operations are not identical. The points are being moved differently. You're asking why this and this is not the same. Is that what you mean?
Yeah, I mean, I know they're not the exact same, but it looks like if you took a 3-1 and rotated it twice, 2 times to the 2/3 position, you'd get the same position as the 1/3 of the 3-2. Or is that not accurate?
No, actually, the 3-2 is the mirror image of the 3-1. Okay.
Oh, okay.
So, and I wanted to get to this point in a moment. So these two screws, which are being produced here, they are mirror images relative to each other. And these two mirror images are not superimposable. Okay, like two enantiomers are not superimposable. Okay, for that reason, you cannot express a symmetry operation associated with a 3-1 axis by a 3-2 axis and vice versa. Okay, if you could do that, then the symmetry operations would be identical and one would not need to describe them separately. So they look similar, but they are not, because they are mirror images of each other. Does that answer the question?
Absolutely. Thank you. Yeah.
Okay, so the last step is that we move this atom here around by another 120 degrees and another 1/3 of the unit cell parameter in the direction of the screw axis. So we'll see that the produced atom sits on top of the original atom, and it's shifted exactly by 1 unit cell parameter. Okay? So therefore, it moves just into another unit cell, but within the other unit cell, it sits at the same position as in the original unit cell. So because all unit cells are identical, we can say, well, in a sense, it has returned to its original position. Okay, and we have actually reached the identity. Okay, so a full translation is always as though we did actually nothing. Okay. So now, what about the other rotation? So now again, we have to rotate counterclockwise, but now we have to rotate by 2/3 of the unit cell parameter. Okay, so that moves this original atom here into this position, elevated by 2/3 of the unit cell parameter. Okay, so now let's carry out the symmetry operation another time. So we will rotate it by another 120 degrees and have to shift it by another 2/3 of the unit cell parameter. So 2/3 plus 2/3, that gives 4/3. Okay, and 4/3 is, well, identical to 1/3. That is because 1/3 plus 1 gives 4/3. Okay, so if we go from the position 1/3 to the position 4/3, we have to shift according to entire lattice parameter. Okay, and this is as though we would only translate, and therefore we have the identical situation. So therefore we can write here 1/3 plus associated with the position of the atom here. Okay, so now finally we need to move by another 2/3 of the unit cell parameter and rotate by another 120 degrees. And then we see that we superimpose the original atom again. Okay. We have now overall shifted, well, 2 full lattice parameters A. Okay, because 4/3 plus another 2/3, that gives 6/3, and 6/3 is the same as 2. All right, so therefore, after carrying out that 3-2 symmetry operation 3 times, we have produced the identity. Okay, now you can, however, view the produced, well, object also a different way. You can say that, well, rotation by 2/3 counterclockwise is the same as rotating by 1/3 into the opposite direction. So indeed, if we just rotate in the opposite direction, indicated by this red arrow here, we would rotate by 120 degrees and translate by 1/3, then rotate it by another 120 degrees and translate by another 1/3, and finally rotate by the final 120 degrees and the last 1/3. Okay, so from this perspective, it becomes obvious that the 3-1 screw axis is actually the mirror image of the 3-2 axis. Okay, and that the produced screws or helices are mirror images to each other. Okay, so now we can go, for instance, to the 4-1. Okay, so in this case, we would need to rotate by 90 degrees and translate by a quarter, and we have to do this overall 4 times to produce the identity. Okay, so for the 4-3 here, we would have to rotate by 90 degrees counterclockwise and translate by 3/4. Okay, so if we did this 2 times, then we would be at 6/4, which would be the same as a half. If we did this 3 times, well, then that would be 9/4, which would be the same as a half, 2 plus a half, 8/4 plus a half. And if we did it 4 times, then that would be basically 12/4 or 3. Okay, so carrying out that symmetry operation would basically translate the atom by full 3 lattice parameters. Okay, but we can still say that it's not as though we have translated at all, because translating by an integer multiple of 1 lattice parameter is also the same as though we did not translate at all. But now, when you look at this image here, that you see that when we actually rotate the other way around, okay, then we translate always by 1/4, here by 1/4, 2/4, 3/4, 4/4. So that overall, this produced helix is again the mirror image of this helix. Okay, and these 2 helixes are actually, well, helices are or screws are enantiomers to each other. Okay, so in addition to these 2, you also have the 4-2 screw axis. Okay, so in this case, you rotate by 90 degrees, and then you translate by a half lattice parameter. Okay, so when you do this 2 times, you shift by a 4 lattice parameter, but that's as though you would not shift at all. Okay, if you do it 3 times, then you do it basically 1.5 times, which is as though you only did it a half times, okay? Because a half plus 1 gives 1.5. And if you did it 4 times, then it would be the same as though you did it twice, which is again as though you wouldn't translate at all. All right. So now for the 4-2, there's no mirror image. Okay, so this one stands on its own. Okay, so now we could also think of a 4-4 screw axis, but that would be basically the same as only a proper rotation. And the 4-5 screw axis would be again the same as a 4-1, and the 4-6 screw axis would be the same as a 4-2. So these would not be unique symmetry elements. For that reason, we would not list them anymore. Okay, and the 4-fold screw axis would be limited to 4-1, 4-2, 4-3. Okay, so now finally, we would also need to consider the 6-fold screw axis. So now we can have everything from 6-1 to 6-5. Okay, for the 6-1, we would translate by 1/6 of the lattice parameter along the direction of the axis and rotate by 60 degrees. Okay, and if we do this 6 times, then we will produce the identity. Okay, now just like the 3-2 is the mirror image of the 3-1, the 6-5 is the mirror image of the 6-1, and the 6-2 is the mirror image of the 6-4. Okay, the 6-3 does not have a mirror image to each other, to itself. Right? So this gives you all the explanations for the screw axes that there can exist. So as you can see here, each of them in crystallography has its own symbol. We already discussed here the symbol for the two-fold screw axis and the three-fold one. So now for the four-fold ones, we have a square, and then we have the respective propeller blades associated with it. So for the six-fold ones, we have 6 propeller blades for the 6-1 and the 6-5 respectively. For the 6-2 we have 3, and for the 6-3 there are 2. All right. So now some of the screw axes, as we have discussed, are chiral objects. Okay, so for instance, the 3-1 and the 3-2 are enantiomers to each other. So that gives rise of a phenomenon which is called enantiomorphism. So enantiomorphism is the counterpart of enantiomeric isomerism in molecular chemistry. So like you can have 2 enantiomeric molecules, enantiomer molecules. You can also have 2 crystals that are enantiomers to each other. And that phenomenon occurs when you have chiral screw axes present in your crystal. So one well-known example is quartz. So you see here exerts from the quartz structure. In particular, you see here corner-connected SiO4 tetrahedra that build a screw axis, and in this case it's a 3-fold screw axis. Okay, that could be either 3-1 or 3-2. Okay, so we rotate a particular tetrahedron around 120 degrees, and then we translate it by 1/3 of the unit cell parameter, and then it's indistinguishable from its original form. So we'll either have to rotate clockwise or counterclockwise. And after we do it 3 times, basically our tetrahedron will need to be indistinguishable from its original form, and we just would need to have translated it. So you see here, when you put yourself on this tetrahedron, that you have to go 1, 2, 3 tetrahedron, and then you see that this tetrahedron is produced by translation from this tetrahedron here. Okay, that tetrahedron here is produced by the first 3-1 or 3-2 symmetry operation. This one is produced by the second one, and that one is produced by the third one, which is the same as the identity. Okay? And of course, we have an extended solid. That means that this tetrahedron is now just in a different unit cell as this one, but of course the screw axis continues because there's another unit cell adjacent to the original unit cell. Okay, so overall you see that this builds a chain of tetrahedron that describes the screw. We could think about whether it's a left-handed screw or right-handed screw, And it seems that we actually have to rotate counterclockwise. And that would mean that we have actually 3-1 screw axis here and not a 3-2. All right. Then the crystal structure of quartz is made of, well, interconnected strands that describe these screws. So we see that on the right image here. So basically, this is your first screw indicated in yellow, and then you have here 4 others: purple, blue, and in green. Okay, and each strand is associated with a screw axis. 3-1 screw axis. So you see that the yellow and the blue tetrahedra, they're interconnected by purple ones here and here, and the blue tetrahedra here connect also the yellow and the green, actually here and here, producing then the overall crystal structure. So in the quartz crystal, you do not only have 3-1 axes, you have also 6-1 axes and 6-5 axes in the enantiomorphic form of the quartz. So you see these 6-fold axes actually here. Okay, so here's one indicated in yellow, winding itself through the crystal structure of quartz. So now, in this case, we will have to go 6 tetrahedra until we reach the identity. Okay, so we can, for instance, start with this one, and then we'll be on the second tetrahedra, that will be the third one, that will be the fourth one, that will be the fifth one. Sorry, I must have made a mistake. So we have 1, 2, 3, 4, 5, 6 translations. Okay, so the 6th translation produces this tetrahedron, and you see that you only have to take this tetrahedron and shift it into the direction of the axis to produce this one. Okay, so all the other 5 tetrahedra here, they are produced by the screw axis, Okay, so this one is produced by rotation around 60 degrees and translation of 1/6 of the unit cell parameter. Here we rotate 2 times by 2 times 60 degrees and 1/3 of the unit cell parameter and so forth. Okay, so now one and the same tetrahedron belongs both to the to a 3-fold as well as to a 6-fold screw axis, and this is and this is actually shown here. So you see all tetrahedron belonging to a 3-fold screw axis in the same color. So for instance, all these are produced by a 3-fold screw axis. Okay, so all the green ones here are being produced by a 3-fold screw axis. All the purple ones, and here also the blue ones. Yeah? But the same tetrahedra are also being produced by a 6-fold screw axis present, and that is indicated by bold colors. So all tetrahedra that belong to different colors but are all in bold also belong to a 6-fold screw axis. So we can start out with these. You see that these 2 green tetrahedra are bold relative to these ones, for example. Okay, and then we have these 2 bold blue ones, which are interconnected to these 2 these bold purple ones, which are interconnected to these bold green ones. Okay, so you can actually go again 6 translations until you produce the identity. Okay, so if you start with this tetrahedron here, that would be the first, the second, the third, the fourth, fifth, and here the 6th translation. So you can see that you can produce this tetrahedron here just by shifting that tetrahedron here into that direction. Okay, and then your screw axis is complete. All right. So from that you can see that with help of the symmetry element, symmetry relations, you can rationalize crystal structures pretty well, even relatively complex one like the quartz structure. And you will learn a lot more about this throughout the course. Okay, so as I mentioned previously, the presence of chiral screw axes in the crystal gives rise to what is called enantiomorphism. So that means that you will find 50% of the crystals associated with one screw axis, and the other 50% of the crystals associated with the mirror image of that screw axis. So when you look into the nature and analyze the shape of quartz crystals, like here and here, these are both single quartz crystals, you will find that 50% of them will have a 3-1 screw axis, while the other 50% will have a 3-2 screw axis, and the two crystals with having different screw axes will be mirror images to each other. Okay? So therefore, also 50% of the crystals will be described by the point group, the space group P3121, and the other 50% will crystallize in the space group P3221. All right, so we have discussed point groups, but not space groups. So I wanted to define what that is. So let us derive the space group from the following overview here. We have learned that we have 7 crystal systems. We have 14 Bravais lattices. Under the exclusion of translational symmetry, we can have the symmetry elements 1, 2, 3, 4, 6, 1 bar, 2 bar, 3 bar, 4 bar, 6 bar, which gives us the 32 point groups. So now we have additional symmetry elements that contain translational symmetry, and these are the glide planes A, B, C, N, D, as well as the screw axes 1, 1, which doesn't really count because it's the identity, 2, 1, 3, 1, 3, 2, 4, 1, 4, 2, 4, 3, 6, 1, 6, 2, 6, 3, 6, 4, and 6, 5. So these additional symmetry elements lead to what is called space groups, of which we also have only a finite number because the number of our symmetry elements containing translational symmetry is also limited to exactly these. Okay, so whereas we have 32 point groups, also called crystal classes, we have overall 230 space groups. And each crystal would crystallize within 100, would crystallize within one of these 230 space groups. Okay, crystal symmetry is naturally restricted to that. Okay. I see we are at the end of the time. I think this is actually a good time to stop. In the next class, we will discuss the symmetry within space groups in more detail, together with the international table for crystallography, which lists all the 230 space groups together with their symmetry element. But let us stop for now and stop the recording.